I welcome you all in this lecture on system model of hydromechanical system, which is a sub module for modeling and simulation of dynamic system course, which you are going through. So, previously we have seen the various independent systems, that is mechanical, electrical, hydraulic, pneumatic, thermal, and in this lecture we will be seeing the combination of mechanical and hydraulic. Okay. So, hydraulic mechanical systems involves the conversion of hydraulic energy to translational or rotational energy or vice versa. Okay. That is, we can have both way, from hydraulic to mechanical or mechanical to hydraulic. And while going through this, as we have seen earlier when we were discussing about linearizing of the nonlinear equations, that the rate of flow of liquid through orifice is nonlinear relation depending on the cross section area of the orifice and the pressure difference at the two sides of the orifice. Now, when we are talking about hydraulic systems, here the flow takes place from say constant cross section area or through the variable cross section area. Okay. So, we need to consider that here. Okay. Now, okay. So, in that module, sub module on the linearizing of the nonlinear equation, we have seen the case when we assume the orifice area to be constant. Okay. So, here first we will like to see if the orifice area is variable, then how what is the relationship between or how the discharge takes place. Okay. And then based on this concept we will build up a model for the hydraulic servo motor. Fine. So, the rate of flow of liquid through an orifice is given by this equation. Here Q is equal to CD, that is the coefficient of discharge, A is the cross section area of the orifice, and here P1 minus P2 is the pressure drop at the upstream and the downstream side of the orifice, and rho is the density of the liquid. Okay. Here if we assume that this rho is constant, then we can rewrite the equation as Q is equal to CA under root P1 minus P2. Okay. Now, here this C is a constant. So, you can see that here Q is function of area of cross section of the orifice and the pressure drop. Again here, as I said, if we are going to consider the general case, then both the area of cross section as well as the pressure drop both can change. Okay. So, when both can change, while linearizing, what we actually do is that we use the principle of superposition. Now, for using the principle of superposition, what we do, first we linearize when only A changes, and then we linearize when only P1 minus P2 changes. Okay. And then the sum we sum both the cases to get the linearized version of the equation. Remember, the principle of superposition is applicable only for the linearized system. Okay. So, this principle of superposition is applicable only on the linearized version of this equation. Okay. So, this way actually we can get the effect for the combined case, that is the case when area of cross section is varying and the case when the pressure drop is changing. Now, to see how it happens. Thus, for changes about the operating point, the slope of the graph of Q versus A. So, first we find out the slope of the graph of discharge versus area of cross section, and of course, this is going to be M1 is equal to say dq by dA, and this will be C square root of P O1 minus PO2, okay, where basically these values are O1, PO1 and PO2 are the values at the operating point which we are considering. Okay. So, from here once I know the value of M1 I can know if I know C and if I know these values, okay, that is the pressure drop as the operating point. Once I know this, I know C, then I can find out M1. Okay. Now, once I have M1, I can just write del Q is equal to M1 del A. Basically, this is a graph which we have seen in case of the non-linear equation chapter. So, this is your Q and this is A, and it is the nature of the graph is something like this, and here is we have the operating point say P. So, basically this is what I am talking to you, that is this is del Q and this is your del A. Okay. So, here our del Q is equal to M1 del A, where M1 is basically the slope of the slope here of the tangent line at the operating point, it is this one. Okay. Similarly, I can draw a plot for Q versus P1 minus P2, okay, and for that I can find out a slope M2 is equal to dq upon d P1 minus P2. So, that is again this case, that is I plot Q and P1 minus P2 here, and this is my plot, okay, and so I can have something like this. All right. So, this is my del Q and this is my del P1 minus P2. Okay. So, from here if I know A0 values and I know these values at the operating point, I can find out the value of M2. Then I can write the linearized version of equation as del Q is equal to M2 del P1 minus P2, and then the linearized version for the combined case can be written as del Q is equal to M1 del A plus M2 del P1 minus P2. Okay. Here M1 is the slope for the first case and M2 is the slope for the second case. Now, next we will be using this concept to see the or derive the system equation for the hydraulic servo motor. Okay. Here I can just describe the system. You have a spool valve here, okay, and this spool valve has got one input port say with pressure Ps and two output port with exit pressure as Po, and the position of or this valve can be operated with the help of this piston cylinder arrangement, and say xi here represents the coordinate for the motion of this piston, yeah, okay. And here you can see that there is a piston inside the cylinder, okay, and the cross section area of this chamber is A, and of course, because of flow of liquid, this will be causing the piston to move in this direction or other direction, and here is my mechanical load. Okay. So, you can see that there is a mass say M, and say there is a damping present say represented by C, and there is a certain stiffness say represented by K. Okay. So, this whole thing spring mass damper system basically represents the mechanical part of it, and here we have the hydraulic part. Okay. So, this we call it as the spool valve. Okay. And of course, as I said, this is our load and the output is basically this XO. So, our aim here in deriving the system equation is basically to find out the relation between the output, that is XO, and the input Xi. Okay. So, this we can work it out, and let us assume that there is a discharge Q from these valves, inlet valve and exhaust valve from here, and the pressure at this side is say P1 and at this side is P2. We will further talk about it. So, now here you see that for the fluid entering the chamber, what is going to be the pressure difference. Okay. So, as I said, this side we assume the pressure to be P1. So, the pressure difference for fluid entering this chamber here is Ps minus P1. Okay. And for the fluid leaving the chamber, the pressure is P2 minus Po. Okay. So, here this side the pressure is P2 and this is the exhaust pressure Po. Okay. O basically subscript for out. So, here the pressure drop is P2 minus Po. Okay. And let the operating point be the central position of the spool valve. Now, at this position, that is the central position here, the ports connecting the cylinder are both closed. At the central position, these ports are closed. So, for this condition the Q is going to be 0. So, whatever be the delta Q or the change will be basically Q minus 0 or it will be Q. Okay. So, the area of cross section of the orifice, as I said here, because when this piston will be moving, the area of cross section will keep on changing here. So, the area of cross section of the orifice is proportional to basically this Xi, okay, if Xi is measured from the central position. Now, also change in pressure on inlet side of the piston is delta Ps minus P1, or this I can call it as minus delta P1, assuming that the Ps is constant. Okay. And the change in the pressure on the exit side of the piston is del P2 minus P0, and I can take it at del P2, assuming that this P0 is say constant. Okay. Thus, for the inlet port I can write this expression basically, okay, which is this expression we are getting from this generalized expression which we have derived basically, okay, that is M1 into del A plus M2 into del P. So, here I can write for the inlet port the Q is equal to M1 Xi plus M2 into del P. So, here minus del P1 for the inlet side. Okay. Similarly, for the exit port I can write Q as M1 Xi plus M2 into delta P2. Okay. So, this way I can write these expressions, and when I sum up both the equations, then this is what we get: 2Q is equal to 2 M1 Xi minus M2 del P1 minus del P2. Okay. Or here Q will be M1 Xi, I divided by 2. So, here minus 0.5 M2 del P1 minus del P2, or I can write Q, I just keep this thing as some other constant. So, I write it as say M3. So, M1 Xi minus M3 del P1 minus del P2. Okay. So, this is the expression for the Q. Now, for the cylinder, the volume of the fluid entering the left hand side of the chamber is same as volume of the fluid leaving the right hand side of the chamber, and this volume will be basically x0 into A, where x0 is this piston motion and A is the area of cross section. Okay. So, A is the cross sectional area of the piston and x0 is the distance moved by the piston here, this distance. So, what will be the rate of change of volume? So, we can differentiate this A x0. So, A, it will be A dx0 by dt, okay, and the rate at which the fluid enter left hand side of the cylinder, of course, that we have already taken it as Q. So, suppose there is some leakage QL through the piston, okay. So, in that case what happens, basically this Q will be A dx0 by dt plus we will be having a term QL, okay. So, this QL actually is something like this. Say we have the cylinder and we have the piston here, okay. So, QL is basically this flow which is being taking place from here, okay. So, that Q will be A dx0 by dt plus QL, and substituting for this Q in this expression, okay, what we get as m1 xi minus m3 del p1 minus del p2 is equal to A dx0 by dt plus QL. So, we have already derived this expression for Q, and here what I am doing is I am substituting this value of Q from here into this equation, okay. So, we get this expression. Now, QL, as I was telling you, can be considered as flow through orifice of constant cross section, because this cross section we can treat this as to be the constant cross section, okay. So, if we do that, the pressure difference across the orifice will be del P1 minus del P2, okay, because this side the pressure is del P1 and this side the pressure is del P2, okay. So, if we linearize the equation for the constant cross section area case, then this Q leakage will be M4 into del P1 minus del P2, okay, where M4 is again the slope of the graph for QL versus del P1 minus del P2, okay. And substituting for QL in this equation, we can put it here. So, what we have is basically m1 xi minus m3 del P1 minus del P2 is equal to A dx0 by dt plus this term. For this QL I am substituting from here. So, it is m4 del P1 minus del P2, and then what we do is we just simplify this equation. So, m1 xi minus m3 and m4, these I just bring it together, del P1 minus del P2 is equal to A dx0 by dt. So, the pressure difference across the piston, as we know, leads to the force exerted on the load, and the value of this force will be del P1 minus del P2 into the area of cross section here. This side the pressure is del P1 and this side the pressure is del P2, okay. So, this pressure difference multiplied by this area of cross section basically will be giving you the force, okay. And considering the stiffness and damping present in the motion of the mass, that is this mass, okay, the net force acting on the piston we can find out, that is this is the force which will be accelerating the mass, okay, or this is the hydraulic force basically minus the force because of the stiffness present, and this is the minus force because of the damping present in the system, okay. So, here, and as I said, this force will is responsible for the acceleration of the mass. So, this net force I can write as mass into acceleration. Okay. And here this is you can see that the second derivative of the xo, fine. Now, we can rearrange this equation. Okay. So, we have del p1 minus del p2 is equal to m by a del square x0 by dt square plus k by a x0 plus c by a dx0 by dt. And now, we can substitute this in this the value from this equation which we have derived, okay, that can be substituted. So, let us see. So, if we do the substitution here, you can see I am going to substitute for del p1 minus del p2 here. Okay. So, if I do this, this is what I get. So, m1 xi minus m3 plus m4, this is the substitution for your del p1 minus del p2 from here into this equation. Okay. So, this plus k by a x0 plus c by a dx0 by dt is equal to a dx0 by dt. Okay. Now, what we do? We simplify this expression further. So, m3 plus m4 m by a d square x0 by dt square. Basically, now I am writing the expression in terms of the coefficients of the derivatives. Okay. So, here the coefficient for del square x0 by dt square is going to be this one, plus here I am just segregating the term the coefficient of dx0 by dt here. So, this a and this term here is going to come, plus we have this k m3 plus m4 by a into x0, and this is going to be equal to m1 xi. Okay. And further I can simplify this, and to do that simplification, basically what I do that here I simplify this term and then multiply and then divide this divide whole expression by this term. So, this is how I get. So, this is I get from here a square plus m3 plus m4 into c, and of course, I have m3 plus m4 into m here. A gets cancelled, basically one a from here and one a from here gets cancelled. So, this is the coefficient of the second derivative term plus dx0 by dt here, plus we have the coefficient into x0 is equal to, of course, here this coefficient into xi. And further, if I write these terms, I give some name for these terms, say alpha d square x0 by dt square, plus you can see here this is dx0 by dt, plus say I write this as beta x0, plus say this as gamma xi. Okay. So, you can see here what I get, basically I get a differential equation of second order, okay, and this equation expresses the relationship between the input displacement xi and the output xo. Okay. And of course, there are various coefficients alpha, beta, gamma, and these coefficients can be evaluated. Basically, here m is the we have the m term, and there are m3 and m4 terms being there. Okay. And this way we can work out this one. Okay. And here m is basically that the mass, and of course, m1, m2, m3, m4 are represent somehow the slopes, okay, which we have derived for linearizing the expressions. Okay. So, with this I would like to close this subchapter, and you can refer Bolton Mechatronics and our book published by Springer for further reading. Okay. Thank you.